Thanks very much. Thanks, Laura, Maria, Liam, Oliver, for putting this together and for the kind invitation. Yeah, I'm a bit of an outsider of algebraic combinatorics, so I appreciate this, you know, in an extra sense. I'm going to talk about some work joined with Esme Bejo and Andres Vindas-Fernandez that sort of, I guess, starts in your world, and I can't help it, and do geometry to anything that you throw at me. Anyway, so let's get started. So this slide I don't really have to put up for this audience, but just to get us started. So this is about graph coloring, proper graph coloring. Everybody in this room knows the chromatic polynomial, and I will have a little bit of a running example on a path on 4 nodes. And so I trust everybody could compute the chromatic polynomial for that graph. But really what I'm interested in is the chromatic symmetric function. And this is a staple in the combinatorial world of symmetric function, produced by Richard Stanley, which is on this slide. It's a vast generalization, again, in the world of geometric functions that recovers the chromatic polynomial if you do this specialization, you plug in n ones and the rest 0. So what are we doing? So here's the definition for my talk. So we have another extension of the chromatic polynomial. So what you do is you fix a linear form with positive integer coefficients. So think of this as just as a vector whose entries are indexed by the nodes in the graph. And then I'm taking this finite sum, I'm summing of all proper colorings, but I'm weighing each color with a q to the linear form evaluated at the coloring. And so I still have sort of the same parameter n that you have in the chromatic polynomial, and that tells me I'm going over n colorings. And a lot of times, a lot of our results are for a special case, lambda equals 1, 1, 1, 1. So in that case, what you're summing, you're weighing each coloring, excuse me, by q to the sum of the colors. And of course, when you set q equals 1, this actually should be any lambda, that doesn't matter. When you set q equals 1, you recover the chromatic polynomial. And maybe more interestingly, when you leave q a variable and you make lambda this vector of 1, so this is what I mean by this boldface 1. I'm not sure how much this is visible. So whenever you see this boldface 1, I'm thinking about the linear form all ones. Then you get an evaluation. It's called the principal evaluation of the chromatic symmetric function, where you plug in q squared and so on up to q to the n. So I'll spend the next 5 minutes trying to sell you why this is a good idea, this definition over here. But let me first throw an example that you would, and the formulas that I'm going to throw at you for the next half hour, they don't really have any meaning other than you see sort of a big mess. So when you compute this, what you see here is you see sort of a rational function in Q, which maybe that's expected, and sort of the behavior in N is not so clear. Okay, so that's really the reason why I'm showing this example for P4. So yeah, so let me first give you sort of like theorem number 1. That sort of gives you and then on the next slide, I'll tell you why we're doing this. So theorem number 1 is the polynomial structure over here. So it turns out this function, is a rational function in Q. but it sort of wants to be a polynomial at n. And so what I mean by that is there exists a polynomial that we call chi-wiggle in two variables, q and x. Excuse me, it's a polynomial in x, not in q. It's a polynomial in x with coefficients that are rational functions in q, such that when you plug in a q integer, you get what I just defined in the last slide. So here's my running example again, and so the message of this example now is that this looks a little cleaner, correct? So you see it's a sort of a it's a degree 4 polynomial in x. Maybe that's what you should expect for a path and 4 nodes, and the coefficients are now rational functions in Q, but even those rational functions are kind of well behaved. They all have the same denominator. Okay, so I should have also said, like, if any point there's any questions, I'm very happy to interrupt. So just yell, or if somebody could watch the chat and then yell at me, I'm happy to stop. Yeah. So why are we doing this? So I already mentioned we're going sort of like in a different direction in the chromatic symmetric function, but there's sort of there's a common a specialization of our definition in the chromatic symmetric function that's sort of still a generalization of the chromatic polynomial. I don't really want to say much more about this. Of course, like this object over here is famous in the world of symmetric functions. To somebody who does so geometric combinatorics and numerative geometric combinatorics, this sort of object is in some sense much kind of multivariate generating function. I compute 3 of them before breakfast. And so the idea is a little bit that we, number one, we milk the fact that we have this common generalization. And number two is, each side and I guess sort of the main point of the top right, why this might be interesting is I have this sort of polynomial structure that, of course, you don't have in the symmetric function. Okay, so here is the main conjecture in the chromatic symmetric function world. This was an original standard paper. The chromatic symmetric function distinguishes trees. So I'm not sure if this is the first reference of this sort of refined conjecture, but it's the first I'm aware of. It's a paper by Nick Lur and Greg Warrington that appeared just this year. It's a stronger conjecture that says this principal evaluation of the symmetric function already distinguishes trees. Yeah, and so in some sense, now you can see sort of like maybe one of our big motivations. So here now I can actually start talking with people in this room, because this is also a special evaluation of what we're doing. This conjecture has been computationally checked for, I think, trees up to 17 nodes. And so now we can ask other questions because we have this polynomial structure. So Nick and Greg did not think, they thought about in the world of symmetric function, they didn't think about polynomials. So now we have a polynomial that goes with this principal evaluation, and so now we can ask, now what about the coefficients? And so we have a refinement of the refinement, and even a stronger conjecture that just the leading coefficients distinguishes trees. Okay, so we have checked this for trees up to 16 nodes. I should also make some remarks about sort of other things in the literature, and this is not everything. So by all means, if you're interested in more background, check out our paper. So our function here, at least for the case where the linear form was all ones, was previously studied in a paper by Löbel in 2007. Maybe maybe even more important, is a recent paper by Logan Crew and Sophie Spirkel. So they have a weighted version of the chromatic symmetric function, which I'm sure many people in this room are familiar with. And those people will not be surprised when I tell you that our construction is a special evaluation of this weighted chromatic symmetric function. Again, so you could say like, okay, a lot of what we're doing should follow from this older work, but we're really focusing on this polynomial structure. And it's, again, not a viewpoint that Logan and Sophie had. I also want to advertise Jose's talk in a little less than 4 hours. He will talk about related aspects.
There's two questions in the chat. I don't know if you wanted to be alerted of that.
Check.
You want me to read you the chat questions?
So the first question is, does it conjecturally distinguish any other classes of graphs? For example, recovering Betty numbers. It's a good question. I'm assuming you mean our concept. So we don't know. We've experimented with a few classes, like, sort of the thing that you do, paths and stars. And I think that, well, paths and stars are both trees. Yeah, so I don't think we've experimented with non-trees. Still a good question. The second question from Maria, does chi lambda also distinguish trees? Yeah, so great question. So, yes, the answer is yes. And so here's maybe one thing, one aspect of this that could be interesting. We can play with lambda. So in this theory, lambda, I think of lambda as fixed, and then for every fixed lambda, I get a polynomial. So I'm going to get different polynomials. But maybe this is where Maria's question is going to. You have some flexibility over here, and so that would be cool to kind of, make use of that. We have not done that competition. Thanks. Good questions. Okay, so where is this coming from? So here's one slide in my world. So for people who know me, they know I like to compute Erhard polynomials. So you start with a lattice polytope. So it's a polytope in some Euclidean space whose vertices are on the integer lattice, and then you start counting integer lattice points as you dilate the polynomial, as you dilate the polytope by an integer, by positive integer dilate. And so Erhard's fundamental theorem is that this is a polynomial. Okay, so there's two reasons why this is interesting for this talk. So number one, here's sort of like my motivating example is what people call order polynomial, which is really which is also an Erhard polynomial of a order polytope. So you're fixing a poset, finite poset, and then you look at all order preserving maps. That's one version, or all strictly order preserving maps from the poset into the set 1 through n. Yeah, and so you don't need Erhard polynomials to realize that these two functions are polynomial, but Erhard, again, they're Erhard polynomials of certain polytopes. And the connection to this whole chromatic world is that you can compute the chromatic polynomials with these strictly order preserving maps. Correct. So if you think of a coloring, each coloring giving rise to an orientation simply by orienting each edge by the color gradient, that gives you a poset because you don't have a cycle. Yeah, and so from my point of view, my very sort of geometric point of view, the chromatic polynomial is really a sum of strict order polynomials, where the sum goes over all acyclic orientations of your graph. And this is not at all a new point of view. In fact, basically, you can find this point of view in Richard Stanley's PhD thesis. Okay, so that's number one. That's connection number one, and connection number two is somewhat recent work of Frédéric Chapoton, who has sort of a Q version of Erhard polynomials. So what Chapoton does is, so this should now look familiar from the third slide. So he fixes a linear form with, an integer linear form, and then instead of counting lattice points in dilates of polytopes, he weighs each lattice point with q to this linear form. And so you need some mild assumptions on the polytope, but if those are met, then again you have this polynomial structure. One variable in exactly the same way as what you saw earlier. You have to plug in a q integer, and then the coefficients are rational functions in q. Is my audio cutting out?
A little bit, but we didn't miss very much, I think.
I apologize. I should have said this in the beginning. So I'm giving this talk from ECHO in Popayán, Colombia. So greetings to everyone from the ECHO world. And I was hoping my internet connection was here safe enough, stable enough.
It's a very good.
Excuse me, Oliver?
A very good connection most of the time. It just cuts out occasionally.
That's great. So now, if you take the last two slides, throw them into a pot and stir a little while, you're going to get theorem number one. So if we apply Chapoton's theorem to order polynomials, to order polytopes rather, and then sum over all acyclic orientations, you get these q-chromatic polynomials. So this is where the sort of first structure comes from. And well, so here's some things that anybody who works on innovative graph theory will probably expect. So there's a deletion contraction formula, and in fact, this is just a corollary of work by Logan and Sophie. So for this deletion contraction to work, you have to now vary the lambdas, correct? So the lambdas, the linear form is indexed by the vertices, and when I do deletion contraction, I assume that you label the edge, the vertices of the edge with 1 and 2 that you delete and contract. Maybe interesting, this naturally extends also to the coefficients of our q-chromatic polynomials. This is not a big deal, but maybe there's structure over here. And then there's an analog of Stanley's reciprocity theorem for chromatic polynomials. So again, many people in this room know this theorem. So Stanley basically says what happens when you plug in negative integers into a chromatic polynomial. And we have sort of a generalization of that theorem in the Q counting world. And here it is. And I should say the same remark about my formulas earlier about the theorems that you're going to see now. You're going to see, something with a lot of, ingredients. And really the point is not to sort of trying to impress you with the messy formulas, but to say like, they exist. And of course, my secret hope is also there might be someone in the room that sees one particular result and says like, wait a minute, I've seen this right hand before. And in which case I would love to talk with you. Okay, so now what about polynomial structure? So we have sort of counting, we have formulas for the polynomials. So now I'm really going after this polynomial now that we call chi-rho, in which you then have to plug in the q integer. in again, sort of like when this slightly looks familiar. So there's sort of Möbius inversion formulas on the flats on the graph, and then they're specialized for a tree. Again, so the details are, the devil is in the detail. My point is we can sort of compute them. And as again, people will not be surprised, you get more sort of structure when you now concentrate on certain families of graphs. So there's other sort of combinatorial objects coming in, which is nice. So now I'm going to zero in further and further. So I would like to now zero in on trees. Yeah. So and I would like to look at the leading coefficient of these polynomials. So as you zero in, the formulas get smaller and smaller. And again, the point is sort of like you can start computing things right here. And now, something funny happens if you zero in now, still for trees, still in the leading coefficients, and then you set this linear form to be all ones. You get sort of two formulas for the leading coefficient, and they're not obviously related. But anyway, so there's various ways of computing things. And so now I actually have a throwback to the chromatic symmetric function. So, on my last couple of slides, you're going to see some other connections. And once you realize those connections, you get the corollary that actually this leading coefficient is again a specialization of the chromatic symmetric functions with actually infinitely many variables. So you get a rational function in Q. And again, so people have looked at that sort of. I communicated with Richard Stanley about this, and he said, yeah, we've looked at these things, but my point is sort of like these evaluations come up very, very natural in this body of work. Okay, and so the last thing I want to talk about is, if you look at the second formula for this leading coefficients, and you've worked with p-partitions, then this looks very familiar, and so that sort of suggests the following generalizations or analog in the world of graphs that I'm not sure has been around, but okay, we'll make it. So so a p-partition is a concept that you have on a post-it, where you look at all tuples of length size of the post-it that sum to n, and the entries of the tuple respect the post-it. So for the people who do p-partitions, I'm using order preserving maps, and in fact I want to do strictly order preserving maps because what are we doing in the world of graphs? Well, we can do the same concept and just say we want the entries of the D tuple, so now D is the number of vertices in my graph, to be different if they correspond to an edge. And so, it's not a big deal. So this, if you now count G partitions, this is just a sum of strict P partitions over the acyclic orientations. And also from first principles, the generating functions of these G partitions are specializations of the chromatic symmetric function. Sort of very, very similar to what you saw on the last slide. If you've computed p-partitions, then this theorem on this slide is not a surprise to you. So this is sort of like theorem number one for G partitions. So there's a way of computing the generating functions of the counting functions for G partitions, and the way to do that is really following the same theorem that you have for p-partitions. So that's maybe not so interesting, but the interesting part to me anyway is how this now fits in with what you saw before. So at least for a tree, you realize that the leading coefficients of our q-chromatic function, again in the special case when the lambda and the linear form is all ones, is basically the generating functions of these G partitions. And so the conjecture that you saw, the conjecture that was a twice refinement of Stanley's conjecture, can be rephrased in the language of G partitions, excuse me. You could now, that conjecture that we said the linear coefficients distinguishes tree, you can rephrase by saying this G partition counting function distinguishes trees. So if anybody is up for computing these things, here's a chance to prove a famous conjecture. Okay, that's really it. So there's more. We have a preprint on the archive, and I would love to talk with anybody who's interested in this. This is, I hope this is not the end of the story for us, and hopefully also not for other people. I'm really interested in applications that other applications that people might have in mind. So yeah, if anyone, especially in your community, has some ideas or some comments, I would love to talk. And with this, I thank you all for the attention.
Thank you. We've got, let's say, 2 minutes for questions. And you can just unmute yourself and go for it.
Okay, this is a quick naive question. Okay, so maybe it's already kind of on the last slide, but like, do you have any like idea about how like this might relate to more things related to like Earhart theory related things, or is it just like it was a starting point and then?
Good question. I mean, that's where we're coming from. So really, I should be honest, correct? So I saw Chapoton's paper a couple of years ago, and I said, "This is really cool. I would like to do something with it." And this is the best I could come up with so far.
That was fun. But I was just curious if you went the other way in any sense, or if you know any like specializations of the generalized like chromatic symmetric function that.
Yeah, I
don't. Meaningful about those, but okay, yeah, maybe
no,
it's
I don't.
little...
But it's a good question.
Okay.
I invite everyone to look at Chapoton's paper and come up with ideas. It's a cool.
All right, thanks.
There's a question from Maria in the chat. She asks if you restrict to particular families of trees, what are the difficulties in showing that the leading coefficient distinguishes things?
Sorry, can you say it one more time? I have it here too.
Yeah,
I think I can say it now. I just have some background noise. But what are the difficulties that arise like when you you have a formula for the leading coefficient now. When you try to use that to show it distinguishes trees, like what are the tricky parts, or are there families of trees that you can distinguish with this new formula or things like that?
There are families that you can distinguish. For example, stars. That's pretty quick. What's tricky is good question. There's a lot of things that are tricky. So our formulas are still a mouthful. So I don't quite know what to do on the theory side in terms of distinguishing trees. And on the computational side is the usual thing. You start trying to be smart, and then at some point you run out of computer time. So that doesn't mean that there's nothing there. It just means that I haven't tried enough, or we haven't tried enough.
Thank you.